Hi guys and girls. In the last classes we saw the simplification of logic expressions by algebraic methods. Now we know that it is possible only for a small number of variables like a 2 variable or 3 variable it is you can do with hand. But if the number of variables is more, we have to resort to a graphical method or a tabular method that is called Karnaugh map method. So let me start with that presentation. So the contents of this video are that you are learning outcomes, then simplification of logic expressions by Karnaugh maps, then one simple example, a detection of a prime number or the circuit design of a circuit for detecting a prime number, then the summary of what you learned. What you will learn in this course, in this video, are that you will learn to simplify logic expressions with the help of so-called Karnaugh maps. Then you will learn to select the min times for pairs, quads, octets, etc. So how we group together the ones and how you arrive at the corresponding min time. Then you will compare the K-map method with algebraic method. Then you will design a 3-bit prime number detector with the help of K-maps. So in the last classes you saw the algebraic reduction. That is possible only when the number of variables is small. When the number of inputs are say 2 or 3, you can do with hand. If the number of variables is more, you use a tabular method that is called a Karnaugh map, named after Karnaugh. So let us consider a truth table like this. Say this is a 3 variable truth table with the inputs say A, B, C, and these are the min times M0 to M7. 4 different patterns are there, like a 0, 0, 0, it's a 1, 0, 0, 1, it's a 1, for 0, 1, 1, it's a 1, 1, 0, 1, it's a 1. So for 3 cases it's a 1. So we have to synthesize this circuit corresponding to this truth table. Now earlier what we did was we wrote these min times and reduced using algebraic methods. Here what we do is just enter these y values in a something called a Karnaugh map, which looks like this. This is a 3 variable Karnaugh map, so there are 8 cells in this Karnaugh map. Either you can draw like this or you can have a transpose of that. I draw in this manner. So suppose I have these variables, I partition these variables A, B, C, with A is the MSB and C is the LSB. So I partition these 3 variables in this way. I put C here and A, B here. So this C can be either 0 or 1. So corresponding to these 2 rows is 0 corresponding to this is a row corresponding to C equal to 0, and this is a row corresponding to C equal to 1. And this AB, this is written in a not in a straightforward manner, but it's a gray code manner. This is 0, 0, 0, 1, then comes 1, 1. Okay, this is A equal to 1, B equal to 1, and 1, 0, A equal to 1, B equal to 0. This is A equal to 0, B equal to 0, and this is A equal to 0, B equal to 1. This is A and B are 1, and this is A equal to 1 and B equal to 0. So that the entry that comes into this cell is M0, that is 0, 0, 0. So M0 should come here, which is a 0. Now M1 comes here, M2 comes here, M3 comes here, but M4 comes here because this is 1, 0, 0, 1, 0, 0. M4 comes here. Why that change? Because that is due to the gray code pattern we followed. This is M4, this is M5, M5 should be entered here. M6 is this is 1, 1, 0, this M7, that is 1, 1, 1. Okay, so I must enter like this: M0, M1, M2, M3, M4, M5, M6, M7. Okay, so accordingly, if you go here, this is 0, 1, 0, 1, 0, 1, 0, 0. So I write 0, 1, 0, 1, 0, 1, 0, 0. Not the change here. I enter from top to bottom. This 0, 1, 0, 1. Then next to 0, 1 comes here at 1, 0, 0. That is M4, 0, 1. Then this is 6 and 7, M6 and M7, that is 0, 0. Now what you have to do is, first you have to go for octets. There is no octet. There is combinations of ones. How many ones come together? Here you can see that some ones come as pairs. Whatever I show in this, I know this is a sum of product expression, so I need go for cases where the y is 1. Okay, so this is a 1 1. You can see that two adjacent ones come here. This I can take as a pair. Okay, this also, this the one I show in red color, that also I can take as a pair, because these come as, if something comes here diagonally, I cannot take it as a pair. Like if a 1 comes here, I cannot take it as a pair diagonally. No, I cannot do like that. Normally I cannot do like that. If they come in the same row or in the same column, you can take it as a pair or a quad. Four of them together. If 4 ones come together, I can take it as a quad. If 8 ones come together, I call it an octet. Okay, so this is a very useful. These are useful tools for logic simplification. So let us focus on this blue pair, the one I marked in blue oval. Here you can, now the question is, what is the min time corresponding to this this pair? Okay, that I can easily look by looking at the corresponding rows and columns. If I look at the row, you can see that it's a 1. It spans in only one row, and there C equal to 1. So this corresponding C contribution is C. And if you look at these two columns, this oval spans over 2 columns. Here these 2 columns, you have to look for the variable that does not change. Okay, the variable that does not change. Here you have 0 0 and 0 1. You see that the LSB 0 changes to 1 here, but this MSB 0, it does not change. This corresponds to my A. Okay, so here I get A and here I get C. So the min time corresponding to this blue oval is A and C. Okay, sorry, A bar and C. I'm sorry, A bar and C, because it's a 0, so I must say A complement and C. Okay, corresponding to this blue oval, it is A complement and C. I will say that again. What I do here is first I enter these y values in the Karnaugh map following a gray code pattern. Then look for octets. There are no octets here. There are no combinations of 8. There are no quads. There are no quads. There are no combinations of 4. There are pairs only. So I see 2 pairs here. One is I mark in this with this blue oval, and these 2 ones I mark with red oval. Okay, now let us focus on this blue oval and try to find the min time corresponding to this. Now if you look here, this happens in one row. That is corresponds to C, because here it is a 1, so it corresponds to the time corresponding there is C. And if you come here, this spans over 2 columns, so there I have to look for the variable that does not change. Here what does not change? This 0, this is 0 0 and 0 1. So the MSB part A does not change, but it's a 0, so I write A bar, A complement and C. So one term is A complement and C. Okay, corresponding to the blue oval is A complement and C. Now what is the one corresponding to the red oval? These are at edges, but they can be taken as a pair, because after this 1 0 0 0 comes. So this is, you can think as it getting wrapped around. So you can see that here the variable that does not change, this is here it is C. It happens in the same row C, and here AB, and as far as AB are concerned, there is 0 0 and 1 0. 0 0 and 1 0, because the first 0 changes to 1, so I ignore that. Second one is B complement, because this C 0 does not change here. So it is not B, it is B complement, because it's a 0, because then that min time has to be a 1. So it is B complement and C. So the min time corresponding to the red oval is B complement and C. So Y should be, no other ones are there, all ones are covered in this. Okay, if a one comes as a lone member, that corresponding min time should be written. Here all ones are taken care of. So once a 1 is taken care of, you don't have to take it into consideration again. So here there are only 2 min times, only 2 times, that is a bar C or B bar C. Here you can see that it is A bar C or B bar C. So this I can take the C as a common factor, and this is A complement or B complement and C, which is nothing but AB whole complement and C. So this this very compact function, if you remember the algebraic expression, this is simpler than the function we realized. Of course, in the algebraic also, if you do some other steps, you reach at this. It is true. And the circuit looks like this. I have A, B, C lines here. This is A, B all complement, or B all complement, that is ANDed with C. Now you can verify this circuit with QUCS. I will show you that. If I come here, I have this circuit. This is AB. This is AB complement and C. So if I run this simulation, I will enhance this a little. If I run the simulation, you can see that you will get the same truth table. You can see that it's 0, 0, 0, 0, that is M1, M3 and M5 alone, the value is a 1, Y is a 1. So this way I can demonstrate that the circuit works correctly and the synthesized circuit is correct. Now let me go back to this presentation. Now let us have another simple circuit. I need to detect a prime number, a 3-bit prime number, say the number, a prime number between 0 and 7. So whenever it's whenever the input is a pattern corresponding to a prime number, the output should be a high. Okay, so the truth table will be 0 and 1 are not primes. So this is 0, 0, 0 is a 0, 0, 0, 1 output should be a 1. 0, 1, 0, 2 is a prime, so this is a 1. Then 0, 1, 1, it's a 1. 1, 0, 0 is not a prime. 1, 0, 1 is a prime. 1, 1, 0 is not a prime. 1, 1, 1 is a prime. So what I have to enter in the Karnaugh map is a sequence 0, 0, 1, 1, 0, 1, 0, 1. So I have to have a 3-variable Karnaugh map just like the previous case, and I have 0, 0. I have 0, 0, 1, 1. So I have 0, 0, 1, 1. Then what remains is 0, 1, 0, 1. So that this is 0, 1, 0, 1. This is M0, M1, M2, M3, M4, M5, M6, M7. Okay. Now here you can see that there are no quads. There are only pairs. So a quad comes if this is also a 1. I can say that this is a quad. Okay. What is a quad? You may be wondering. So that is if this 0 were a 1, I could construct a quad like this, 4 of them. But unfortunately this is a 0, so I can have only pairs. So what is this? I mark them, these 2 pairs with blue and red ovals. And if I look at this, let me focus on this red or blue oval. You can see that it spans over 2 columns. You can see that this is changing, both are changing. There's only one variable 0 that changes to 1, so I ignore that variable. This happens in one column alone. So what happens is this 0, 1 is taken as such, which is A bar B. Okay. In this column, this A bar B remains the same. It is spanning over only one column and 2 rows. So in this row, in these 2 rows, C is changing, so I ignore that C. What remains is A bar B, so it is Y equal to A bar B, that is one term. And what is the term corresponding to this red oval? If you see here, you can see that it happens in one row, so the C remains constant. C is there, C, and what happens here is AB, it is 1, 1 and 1, 0. You can see that A part is not varying. This 1, 1, 1, 0, this LSB part is varying, but MSB part does not flip. So I should say this is A and C. Okay, A is 1, C is 1, so it is A and C. So A bar B or AC. Okay, this you can see that this is in agreement with the earlier algebraic manipulation. This we did with Q, so I don't do that again. So this is how you do the entry in a 3-variable Karnaugh map. So what you learned in this session, or you understood the logic simplification by Karnaugh maps, and you learned to select min times corresponding to pairs, quads, etc. Yeah, quads, octets, etc. we will see in the following classes. Then you verified the truth tables of the synthesized circuit. So 2 circuits you saw. Then you designed a 3-bit prime number detector and you tested with QUCS. Okay. So that is the end of this video. I thank you all.